midterms. I posted the previous year's midterms. So if you take a chance to, you should take a chance to look at their practice there over the next week. As I said, the time crunch will be quite real. So time yourself. Okay, good. If there are no questions, let me continue. Let's talk about an interesting system. So we've learned about quantum rules, we've learned about how to get measurements, how to describe a system, how to build an observable, and how to do time evolution. And then we applied that to one very interesting system last Wednesday, which was the system of a linear polarizer. So then we derived Melis's law from the laws of quantum mechanics. Okay, so let's talk about another interesting feature, which is this like superposition in quantum mechanics. The fact that you can have different states existing at once, and then you could have things like interference. You know, two events or two realities could constructively interfere and then build up, and two events conversely can destructively interfere and vanish out. This actually should not be unfamiliar to you if you study waves, waves in a pond, for example. So there is also constructive and destructive interference. But let me describe it in the context of this setup. This is called the Mach-Zehnder interferometer. Not entirely sure when it was introduced, probably in the 20s or 30s by Mach and Zehnder. Okay, so what's the setup? Setup is this. They imagine or they build a device in which there are two halves to the system, top and bottom. And then they're going to use some light, some photon. So because there are two halves of the system, right? So because there are two halves of the system, then we're going to have, we're going to denote that the top half is denoted by up and the bottom half is denoted by down. So what these states are the states of photon. And because being in the top half versus the bottom half is classically very distinguishable, so of course we're going to model it as the two states being orthogonal. And by convention, we treat states as normalized. So that means to say that light in this system can possibly exist in either the up or the down state, or somewhere in between, which means that it can, have character in both the top halves and bottom halves. Let's imagine a scenario where we prepare light deterministically in the top half. So we're going to set it down this way. So that means that initially the system is prepared in this state. Okay? And then what's going to happen is that, thank you. Up, and so my initial state is a photon living in this top half. Then they're going to set it down in this direction. And over here, the Mach and Zehnder thought of putting an element which allows light to get split into two parts. Should I keep using the rod? Keeps turning off. Okay. Bear with the technician. Hopefully it stabilizes. Can you guys see it? It's okay?
Yeah.
Sorry about
Okay, so he's going to introduce an element here. I'm going to draw it by this diagram. So this is called a beam splitter. As the name suggests, it is going to split the beam into two parts. Okay? What it is physically is really just a half-silvered mirror. Meaning to say that it's a piece of glass with a little bit of silver on it. So it's partially reflective and partially transmissive. Okay? Yeah, thanks. It's a partially reflective, partially transmitted. So how, okay, before I describe the math behind it, let's keep going on the setup. So when I say partially, actually, it doesn't have to be 50-50. It's not like 50% of it bounces off and reflects, 50% transmits. It depends on how the material is designed. So if the experimental makes it very silvered, then it's 100% reflective. If it's not very silvered, then it's clearly going to be 0% reflective, 100% transmissive. So there's some variability in how we design a beam splitter. And this is really up to the experimental's design. This is some parameters that we can design in the lab. Right? So we'll see how this is modeled mathematically. So okay, so then what's going to happen is that the beam is going to get split into two halves now. So at this stage, in general, then the light has character in both halves, top and bottom. It's going to be in some superposition. Now, at this point, we're going to imagine that there's a mirror here. The mirror is nothing more than just something to bounce the light off so that it can come back to itself. And then Mark and Xander said, well, when the light comes back to itself, let's put another beam splitter here. It could be different, but for now let's assume it's the same. So if you only consider the bottom half, then again there's a chance of it going up, there's a chance of it going down. But if you consider the top half, there's a chance of it going up and a chance of it going down as well. So you see that if you ask, what's the chance of it being up here? It could come from two possible scenarios, either this path or that path. And that's where the interference appears. That's where we can get interference. Okay? We can see that it turns out that in some scenarios, the two paths that both go up could interfere in such a way that the amplitude goes to 0. So essentially you get 0 light on the top and all the light on the bottom, and vice versa. Okay? So in general, you have this scenario. At this point, to ascertain if the light is in, so let's call this BS1, or beam splitter, not bullshit. And let's call it BS2. Same thing, right? And then we're going to have a detector at the end of it. So what it is just a measuring device that measures if the beam, if the light is up or down. So it detects. So it's the detector. So you should really think of this entire box as detector. Okay. At this point, that's the basic, these are the basic elements. There'll be one more element that I'll introduce in a bit. It's called a phase shift. But let's look at the BS's first and the detector. Okay, let's start with the detector. What is a detector? It is going to decide if the beam is in up or down, right? So if I ask this question to you, what's an example, how would you model the detector. So we know that the detector is going to do a measurement. And so the measurement is going to be denoted by a emission operator. You're going to use emission operators to measure things. Could you design one for me? Like, suppose I want the detector to ping 1. Okay, suppose I ask this question. I want the detector to ping 1 if I see up, and I ping -1 if I see down. So this is the up detector, the down detector, and then there's some, it couples to some readout, and this ping could either be +1 or -1. So every time you send a photon, one of 2 events will happen: ping up or ping minus, ping +1, ping -1. But how do you model that mathematically? What would be the operator? What would be the observable? What is the observable? Anyone? Anyone? Yes? Any guesses? Or we can just stare at each other.
Is it +1 up, -1 down?
Okay, very good. Why?
Because if it's up, then it will return a +1. That means, and because it's orthogonal, the down component is cancel out.
Yeah, exactly. So we're going to design an operator, or the observable will have the spectral decomposition where it pings +1 onto the subspace spanned by the projector up. And then it's going to ping -1 if it sees the projector, if it sees the space, in the subspace down. So let's ask the question, why does this make sense? Because, you see, you can ask, what are the probabilities of seeing ±1? So according to the Bond rule, which is a rule that we learned from measurements, so if at this point after the beam splitter, the state of the photon is now psi prime. Okay, so initially this is psi, let me put psi 0 to denote that that's the original state. Is undergoing a few transformations. So after the beam splitter is going to get transformed, then after that it's going to get transformed again, and so then you get a new state here. So at this point, the observable is going to measure something of this state, and according to the Bond rule, the probability of observing a +1 of this observable is just related to the overlap of this state in the up basis, because this is again, this is the same notation, the projector onto the up state. And similarly, projector onto the minus, the probability of observing a minus would be psi prime of gamma mod squared. And that is psi e gamma theta. So don't forget that because the photon can only exist in one two possible states. At the end of the experiment, we know that it should always be of this form: C up, plus C down, down. Simply because up and downs form a basis. So currently we don't know what the C up and C downs are, but we know that they should be there. And if you look at this expression, what this P probability of observing up is really extracting the component in the up direction, which is C up, and taking the modulus squared. So this is the C up squared. This is the C down squared. So as the math shows, it agrees with our physical sensibilities, is really just measuring the component along the up direction and measuring the component along the down direction. If you add the two of them up, they add up to 1, because the state, being physical, has to be normalized. Okay? Yeah, I mentioned something in my announcement yesterday night. Some of you are still thinking too much in terms of real vector spaces. You keep forgetting that you have complex conjugate stuff when you form the graph. Okay, so please, I don't want to see things like, what's the probability of observing an up? And you write C up. Okay, I'm going to mark this as wrong. Okay, because first of all, the C up can be complex. When you square, you get a complex number. What does it mean that your probability is complex? Okay? So no, it's always mod squared. So quantum mechanics is inherently a complex vector space problem. Okay, so that determines the observable, the detector. Okay, so that's nice. Let me tabulate this. So the detector is modeled by O is equals to up, minus down. Okay, let's go back to the beam splitter. So what's happening here? How do we model this event? Something that happens here. Now we learned in the fourth part of quantum playground that yes, time evolution is generated by a Hamiltonian, which gives rise to a time evolution operator. But what I'm going to analyze here is I'm going to ignore the full details of the Hamiltonian. Like assume that there's some Hamiltonian that governs the interactions between the light and the medium or the silver mirror, whatever it is. I only need to care about what happens before and after. So ignore the Hamiltonian. I just want to ask what happens before it enters and after it enters. So because we know that the light should remain some light here, and the the norm should remain 1 on the left and on the right before and after. So this beam splitter should be modeled by a unitary, right? So here's one example of a beam splitter. In the case when the beam splitter is 50-50, meaning to say that 50% transmission, 50% no transmission, reflection, then imagine this. BS, this is one operator. If I send light coming from the up direction, then maybe you might say, I want to model it as 1 over square root 2 up plus 1 over square root 2 down. Okay, so this indeed models the set scenario 50-50. Because then you get a linear superposition of up and down, and you ask about the relative weights between up and downs. 1/2, 1/2. Don't forget that you have to mod square the amplitude. to get the relative weights, right? Okay, then we also need to give instructions on what happens if instead you send in light coming from the bottom. In this scenario, I've assumed that light is coming from the top, but you can imagine that with the same beam splitter, you might send the light from the bottom. So we need instructions as well, what it does. Okay, here's one logic that you could use. Let's say, if it's 50-50, maybe it does the same thing. It sends it 50% up and down, plus 50% up. Okay, now let me ask this question. Is this sensible? Does this make sense? It's a conceptual question. Like, then some of you might be puzzled. What the hell do you mean by does it make sense? Alright? Okay, so what I mean is that, look, I said that this operation should be a unitary because that's the one that governs evolution of states. It sends us a physical state to a physical state. So whatever you propose here had better be unitary. So let's check. Is it unitary? This is 100% a question that will appear. Okay? So let's ask this question. Here I've given you the complete instructions of this operator Vs. My question for you is, I'm asking you if it's unitary. How do you check that? Yes?
You take the adjoint and multiply together.
Take the adjoint of Vs, right? How do you take the adjoint of Vs?
Vector.
Yeah, but okay, so can you help me? What is Vs diagram? How do you write this? Yeah. So okay, I'll write it out. Whatever you say. So what's the object? What should I write here? Okay, so before we even answer the question, what is Vs adjoint? What is Vs? Okay, well, the instructions are there. Look, I told you that if I give you instructions of an operator on a complete set of bases, you should be able to tell me what the operator is. For example, in dyadic form. Okay, so here's a question before this question is unitary. Write down Vs in dyadic form. If you want, another question, write down Vs in matrix form. How do you do that? So you want an operator written in dyads, right? Outer products, which reproduce this behavior, right? So why not this? Okay, if I write it down now, you will say this seems so obvious, but see if you can come up with the logic yourself. So Vs would be, according to the first line, taken up and spit out up plus down. So that's the first line. The second line says, taken down and spit out up plus down. Okay, so let's check. This is your proposed dyadic form. If I apply up onto that, the second term doesn't do anything, second term vanishes, then you get the state exactly as written. If you apply down, you get the state. So we solve the problem. And you now at this point, I think you think, okay, this is very obvious. This is really instructions. You're just trying to ask If I send it up, I get this. If I send it down, I get this, which is exactly those two instructions. Okay, and then if you can do a bit more massaging if you want to, so we can open everything up. The 1 over square root 2 is a common factor. We get up, up, plus, down, up, plus, up, down, plus, down, down. Okay, so that's equivalent, perfectly fine as well. And then now we can ask the question, what is the matrix representation of this guy?
Small 1 over square root.
Everything is 1 over square root 2. So in the basis, the matrix rep in the basis of up and down is equal to 1 over square root 2, 1, 1, 1, 1. Very good. Okay, so now we can ask the question, is it unitary? Okay, some people are shaking their heads. How do you see that? Just calculate, right? Okay, you get BS diagram.
Yes, that is just C.
It's the same thing. 1 over square root 2,
Yeah.
1, 1, 1, 1. And so you do BS diagonal of BS
It doesn't define it.
is equals to 1 half times 1, 1, 1, 1.
Yeah.
Which is not 1, 1. Okay. Okay, so it's not unitary. So this way of modeling it is not correct. Did I make a mistake? I guess maybe it's actually just this, right? Yeah. Okay. Okay, so clearly this is not right because this beams with a destroys state. Another way to see this is that if you were unitary, it would take in a physical state and send it to a physical state. You'll never destroy it. So another way to check that it's not unitary is that conjure up a state where you apply BS onto it, it gets destroyed or its norm vanishes or it shrinks. So basically, I'm trying to say, find a state where BS acts on it and becomes non-physical. Then clearly it's not a good operation, not a good unitary. Here's one example. Take the state 1 minus 1. If I add on it to BS, that vanishes, 0, 0. So that means that if I send in light, which is a superposition of up minus down, equally, then suddenly light disappears, which doesn't make sense. Light has to come out somewhere. Okay, so we've established that BS being modeled this way is not good. How do we rectify that? We can still demand that it's 50-50, but one way of rectifying that is to put a phase here. Let's put a phase here. Let's put a phase here. Minus down plus 1 over 0 to up. If you look at these instructions, it is still saying that I send it to 50-50 character. Because don't forget that if I ask the question, how much component is there along the up direction? It is 1 over square root 2 mod square, which is 1 half. How much component is there in the down direction? It's minus 1 over square root 2 mod square, which is still 1 half. So it still represents a 1 half situation, a 50-50 situation. It's just that there's a relative phase between the up and down. This phase is minus 1, which you can write as e to the power minus e to the power of I pi. Right? So that, like, that's the relative phase between the up state and the down state. Good. If you do that, let's go back to our question. What is BS in dialectic form? We can do exactly the same thing, but it's a relative sign here minus. Now, if you expand everything out, we get that this would be minus. And then this would be minus. And then Okay, BS dagger is minus. But now, if you do the working, what do you get? You get 1, 0, 0, 1. Do you agree? Ever following? Okay, so this is a good unitary. Okay, few comments. The unitary is, this is just one example of a perfectly good model of a beam splitter. And these numbers reflect my condition that it's a 50-50 splitter. But you could have many 50-50 splitters, and you could have phases that imparted here. So you could change the coefficients here. There's a great degree of freedom in what the coefficients can be here. Still retaining unitarity, the matrix is still unitary. And it will also still model a good beam splitter. The only difference is that the material is doing something different. Right, so I'm just saying that depending on the physical material that you have a wide array of beam splitters that you can realize. This is but just one of them. But regardless of whatever you realize, all of them had better be a unitary. Because if it's not, then you're not modeling correctly. Here's another example of a beam splitter. Say that this beam splitter was more biased towards transmission than it was towards reflection. For example, if I do not silver it too much, then it's pretty transparent. So here's another example. BS, till the instructions could be, if I see it up, I'm going to send it mostly up as well, transmit it. So maybe this is like two-thirds up, and then 1/3 down. So then there's only like a 1/3 component that's 1/3 down, wrong way. Because if I transmit, then it goes from up to down. So maybe I want to say that there's more transmission, more with transmission, and BS tilde would be, say, if I transmit from bottom, I want it to go up plus 1/3 down with minus sign. Okay, so this is again a legitimate beam splitter, right? But the only difference between the first and second is what material you're made it out of. Therefore, one is more reflective, one is more transmissive. Okay, but all that are experimental details. We're not taking that into account, but we're just assuming that we're given a beam splitter. For now, let's assume that the beam splitter that we have is modeled by this operation. So this beam splitter is modeled by sending up and you're getting up plus down, and beam splitter down is modeled by 1/√2. What is it? Down minus plus 1/√2 up. Okay. So let's assume that both of them are the same as well. BS1 is the same as BS2. So the same material, the same components. Good. Okay. Now let me ask this question. Given that the light originally was up, it gets sent into this beam splitter. They split according to these rules. Then what the mirror does is just simply to bend the trajectories back. So don't worry about mirrors. It's not imparting any phase shift or anything like that. It's just bending it back. Okay? It's just a convenient way of saying that the trajectories can come back. They come back, and then they can interfere at the second beam splitter. So what's the probability of now observing up? observing up is the same as observing the eigenvalue plus 1. Okay, so here, how do we solve it? Okay, so what do we need to do? We need to say that at this point, as I wrote down previously, the probability of observing up is the final state, the overlap of the final state in the projector up. Agreed? But how is the final state related to the initial state? This is the final state. How is it related to the initial state? Well, the initial state is up. It gets hit by a beam splitter in the second one. So it must mean that the final state is ds, and the initial state, which happens to be ds squared and up. Maybe I should have collated the ds again. So ds in matrix form was 1 over square root 2, 1, 1, 1, minus 1. Do you agree? Okay. So anyone want to tell me what's the final state? It's just a computation. Nothing hard. Right? Just literally just apply it. Okay. So let's look at this matrix form. ds squared is 1 half times 1, 1, 1 minus 1 times 1, 1, 1 minus 1. But that is just 1, 0, 0, 1. That's just the identity. Because another way you can see that is that ds is unitary and its adjoint is itself. So if you know that bs dagger bs is identity, but bs dagger is bs, so bs squared is identity. Okay, good. So then we end up. So in this particular scenario, the probability of observing up is overlap of up with up mod squared, which is 1. So that means that with 100% certainty, we will see the ping in the up detector. We will see the detector only pinging this way. And not surprisingly, probability of observing down is 1 minus p of up, which is 0. As it should be. Okay? So think about what's happening here. It's kind of funny, right? Light has been split. And if you use a classical argument, you would say, alright, there's a 50-50 chance of seeing light here. It comes back. There's a 50-50 chance that, okay, so assuming they came from bottom, there's a 50% chance it goes up. Assuming it came from the top, there's a 50% chance of going up. So I would argue that there's a 50% chance of seeing up classically. But no, this is not what happens. What happens is that due to interference, due to the nature of quantum mechanics, you get interference and you get completely constructed interference along this path, and destructive interference along this path. Okay. Now let's add an interesting complication. Okay. So I'm going to now add an external device, which is called the phase shift, and I'm going to add it, say, here. So sorry for the mess, but essentially I'm just trying to box a region of the trajectories and say that I'm going to introduce a medium here, some sort of like crystal, prism, whatever it is, that will slow the light down. Only on the top half, not the bottom half. So this is called a phase shift. going to now slow the light down on the top relative to the bottom. How much the phase shifts by depends on, again, the material in question. But what we do know is that this guy again has to be a unitary operation, because whatever light we send through here has to again be a physical state. Let's model it by this operation. V, I'm going to call the phase shift V, acting on the up configuration here, gets imparted a phase e to the power pi phi up. And the V, because the V is here at the bottom, is a do nothing operation. So V acting on down does nothing to down. Okay, so I'm saying that this entire box is the V operation. And the V has two actions. Slows, it imparts a phase here, does e to the power pi phi, and here it imparts no phase. So it just returns the same state. Can we check that V is unitary? Yes, no? So one question I can ask is V unitary? I claim that the action of V is this, guys, but does it represent a unitary operation? Yes or no? Yes. No. Maybe. 50-50. Position. Okay, so let's again repeat the analysis that we did to the V splitter. Let's write it in dialectic form, or not. So what is the dialectic form of V? Again, it takes in up, it spits out up with a phase. So therefore, it takes in up, it spits out with a phase. And then, in the second set of instructions, it takes in down and spits out down with no phase. Okay, that's all it is. Now let's do a V diagram. Let me not go into the matrix representation. Let me just do a V diagram directly here. If I do a V diagram here, okay, I apply a diagram to everything, but I swap the ordering. So if I do it step by step, I get this. Up, dagger, down, up, dagger, and e to the power pi phi, dagger, plus, down, and then what I use the fact that the cat is turned into a bra, the bra is turned into a cat. And for complex numbers, the adjoint is just complex conjugation. This is minus I phi here. This becomes down. And lastly, let's compute V diagonal V. And then you can see that if I apply V diagonal and V, then because the terms are diagonal anyway, the only terms that survive the product as well. This up hits this up. But when it hits this up, then it sees the phases. The phases cancel out. Right? So it's e to the power I phi, e to the power minus I phi, that's 1 times up. And then secondly, this is down. And this is nothing more than the resolution of the identity. Okay, so again, this is a unitary operation. Very good. I mean, I would 100% test you on the logic of this. Construct the dialectic form, given the action of the unitary of the operator on basis states. Right. Great. Now that we've introduced a new element into the setup, we can repeat the question. What is now the probability of observing the photon in the up state at the end of the experiment? Again, what is probability of seeing up? P of up, which is the same as P of 1, is psi prime up squared. But now psi prime is different. Is equals to, we gain from the initial state psi 0. It sees the first beam splitter. It gets evolved according to the beam splitter. And it sees a phase shift V, which, let me add an extra detail here. I know that this depends on phi, right? So this beam splitter is a function of phi. And then I will apply the beam splitter again. Agreed? Because after it's being phase shifted, the two paths come and then they collide again, and then they interfere at the last beam splitter. Okay. So this is what I need to do. So to answer the question, I need to do this calculation then. So let's just do it. Okay? I mean, it's just calculation at this point in time. Conceptually, you just set up everything, and in practice, do it quickly without mistakes. So here's a quick and easy way of doing it. Okay? So nothing wrong with doing it in dialectic form, matrix form. Let's do it in matrix form, since many of you are familiar with that. So Bs is given by this matrix. So let's do the first phi first. This is 1 over square root 2, 1, 1, 1 minus 1 times 1, 0. Because my initial state was up. My initial state was up. 1, 0 just picks up the first component, the first column. So this is 1, so it's square root 2, 1, 1. That's what it means to do matrix multiplication. Pick up the first column. Right? Okay, so now we know that the state at the end here, so if you consider this a new state, the state is a linear superposition of 1 and 1, as it should be, because the action of Bs is going to make it into a linear superposition. Now I apply V onto this new state. This V is given by the matrix form, Pi, phi, and 1. Hopefully you can see that, right? Because this V imparts a phase of either I phi, the first component, and 1 on the second component. So now, if I act on that with 1 over square root 2, 1, 1, that's equal to 1 over square root 2, Ei phi, and 1. Nice? And lastly, I can act again with this beam splitter 1 over square root 2, 1, 1, 1 minus 1, and 1 over square root 2, e power I phi, 1. Okay, let's shift the calculation here. So I will get e to the power of I phi. Okay, so the way I do matrix multiplication is that I interpret this first guy as picking on the first column, and the second guy is picking on the second column. So we get 1 half e to the power of I phi, e to the power of I phi, plus 1 half 1 minus 1. So I don't do the having to fit all the numbers together. I just read it off like this. Okay? So this equals to 1 half e to the power of I phi plus 1 e to the power of I phi minus 1. Good. To make it a more pleasing form, let me pull out a common factor of e to the power of I phi over 2. And that becomes e to the power of I phi over 2 plus e to the power of minus I phi over 2, e to the power of I phi over 2 minus e to the power of minus I phi over 2. And why is that nice? Because now this is just cosine. So this is just e to the power of I phi over 2 times cosine phi over 2. And this guy will be I sine phi over 2. And then, if I want to convert that back into dyadic form, I just read out. So this is equals to e to the power of I pi over 2 cosine pi over 2 up plus e to the power of I pi over 2 I sine pi over 2 down. Okay. Agreed? Okay, nice. So we have computed this. This is the hardest step, I guess, technically. Then the next step is actually quite simple. We need to extract the component along the up direction. So we see that phi prime up is equals to e to the power of I pi over 2 cosine pi over 2, and therefore modulus square of this overlap is just cosine square pi over 2. This also means that the probability of observing down is 1 minus z, which is sine square pi over 2. Good. So if I plot the graph, if I plot probability of observing up and along phi. So phi is a free parameter of the phase shifter. It tells me the phase shift. It does this, starts from 1. And then the other one starts from. And this guy is P of. It's meant to be symmetric, I'm so sorry. Everybody not very good at drawing.
Professor,
Yes.
I don't understand why do you write the bra side bra of side and bracket to the this form. Because if you write that, then isn't the face need to be conjugate?
Oh yeah. So okay, so I skip a few steps. This guy is indeed this object times its conjugate, right? So mod phi up is equals to phi up star times phi up. We know that this is e to the power of I pi over 2 cosine pi over 2. What's the conjugate? E to the power of minus I pi over 2 cosine pi over 2. Did they cancel?
But then the earlier one you still haven't mod it yet.
I'm sorry.
You still haven't mod squared it.
Yeah. So you mean here?
Yeah, so I don't understand why do you need to write in this specific and not the direction first.
I'm not sure I understand your question. Like, what do you mean direction first?
Yeah, why can I write in reverse form?
Reverse.
Set a convention in writing in this in the sign first and then the basis.
Ah, okay. So if you want to compute this, I just note that this is the same as up psi prime mod square.
Yeah.
So it doesn't matter, right? It doesn't matter which one.
Preference in writing in that way and not writing in.
It's just convention. I write it this way because the expression that is most sensible is the projector onto the up state. And then this guy is up. Right? And then I just took the left one first and then conjugated the right one. But you could take the right one and then conjugate the left one. That's just your preference. Right? At this stage, this quantity is independent of the way you order it, whichever way you want. Okay, what's the long story short? It's saying that this, depending on the phase you impart on the top branch, you can tune the relative weights of seeing up or down at the end of the experiment. Previously, without the phase shift, we solved the case and we saw that there was probability 1 of seeing the up, which is indeed this point, right? This was the previous case that we saw, when phi was 0. But you see that as you crank it up, or you introduce a material which slows things down, then you can introduce some interesting interference effects. Can I ask, what's the value of phi such that I will see 50-50 up and 50-50 down, 50 up, 50 down? So I'm asking, what is this value? That's 50%. Anyone? 5 by 2? Yeah, exactly. Yeah, it's just you're asking cosine square something over 2 is 1. That's pi by 2. This is pi by 2. This is pi. This is 3 pi. And this is 0. And I'm so sorry for the lousy graphic. This is actually one half. Equally, but I draw it very lousy. Okay. Okay. Let me spend the next 1 minute, 2 minutes, hopefully, talking about something interesting. More conceptual than anything. Just to whet your appetite. Okay, so what happens if we had analyzed this classically? What happens instead if we analyze it? Classically. So let's model again the beam splitter as a chance that after the light is set in, after the beam splitter 1. So there's a chance that after beam splitter 1, this is equals to 0.5, 1 half. And probability of after BS2, BS1 is equals to 1 half. Probability of the state being up after BS1 and down is 1 half. Let's ignore the phase shift. So let's set the phase shift to be 0. Then, as I said, then we can ask, what happens here? What do I see? So what do I see is this. I can argue this. In the event that my beam came from the up, then there's a chance again that I see up after BS2, conditioned upon seeing it in up. This is a conditional probability. What I mean to say is that I am conditioning on the event that it came from this branch. And I'm saying that if you assume it came from this branch, then there are 2 possibilities. That's 1 half. And P of up after BS2, given that it came from the down branch, is 1 half. And similarly, probability of down after BS2, given that it came from up, is also 1 half and so on. But if I am interested in the question of what's the probability of up at the detector, then from this picture, it's clear to see that, okay, let me erase some things. Let me erase things there. So it's clear to see that what you should be doing is that you just ask, what's the probability of being in one of the paths? So there's one path here. We can go up. You can do this. And the other path is this path. So these 2 paths give rise to both events being up. So the probability of detecting up at the end of the day is, if it turns out to be in this path, you multiply it by P of up and after BS1 times, now that you're in BS1, you ask about what's the probability that you see up after BS2, given that you have up before. That's the meaning of the red path. And then you add also the probability of that you are in this down path, blue one, after BS1. And then the probability that you observe up after BS2, given that you're down before. So given that you came from this down branch. So that's the blue branch. And then you work it out. This is 1/2 times 1/2 plus 1/2 times 1/2, and that's 1/2. And so classically, you would say that the chance of saying up should be here. This is classical. This is quantum. Okay. So what's really different here? I'm sorry I'm eating the tutorial time, but I think this is fascinating. So now let's come back to the quantum case and reanalyze it. Don't forget that P of up, P of seeing up at a detector is given by the mod square of, now I'm going to use your friend's notation and swap it around. I go from my initial state, psi 0. I pass it through the beam splitter. Then the beam splitter. Because here I'm assuming there's no phase shift before I end up with the path up and then mod square. This is how you do it computationally. But there's a nice interpretation of it. Let's insert at this point the resolution of the identity. Up, plus down. That doesn't do anything, that's fine. But then what ends up happening is, you can rewrite it as up, ES, up, ES, psi 0, plus up, BS, down, BS, up, BS psi 0. And then we again have the same interpretation of different paths. Because if you trace it out, you begin from one path, from the initial state, psi 0. You undergo the BS, and then you end up in the up path. So that's the red path. Like, this is the red path. Because after you undergo the up, after you get evolved into the up state, and the up state hits the second beam splitter, and then you're asking about its eventual fate into the up detector. And this is also the blue path. This blue path is this one. It goes from the initial state, goes in the down. After the beam splitter, goes in the down. Then it goes through the second beam splitter, and it goes in the up. So, in some sense, the two formulas look very similar. But what's really different is that here we are summing over the probabilities of the different paths. What this is not the probability. This is the probability amplitude of being in this path. Going from up to up, there's a amount that is being transmitted. Now in this case, if this is up, this is just 1 over square root 2. Going from up to up is again this component, 1 over square root 2. Here to here, up to down is 1 over square root 2. And then up to down to up is again 1 over square root 2. So we get, this is mod 1 over half plus 1 half mod squared equals to 1. And this is really the interference. This is the interference. There's one amplitude along this path. There's another amplitude along this path. We are not taking the mod square of each one of them separately first and summing them. We are summing them first before taking the mod square. And because we are summing them first, they are in general complex numbers and they can cancel each other out. Okay? So this is why in one case we get 1, in the other case we get 0. And for those of you who are experts or who wish to know more, this is nothing more than the finite market theory. So quantum mechanics is nothing more than just summation over all possible paths that something can take. But we don't sum the probabilities of that happening. We sum the probability amplitudes. And then only at the end of the day do we take a mod square. Do we find the probability of that? Okay, that's it. Let me invite the TA to come to flash the tutorials for the last half an hour. Hopefully there's time to do some things. Okay? Please. is, but in terms of Oscar countries, how often do you see it? If you know the influence now, you know for sure what's going to happen. This phase is the same for both formats. You saw that this phase vanished. You only get examples. Most square you just saw the relative phase. So suppose that phase shift is crystal crystal one. And suppose that phase shift is then what will matter is one the reason why
小缝后面，所以我们怎么说？因为对于这个方面来说，我们其实一直都没有看的，中间可能我们没有看，只是最后看的。对，但是如果你说换小球什么的，我们一直看这小球，都没有看懂什么意思。一直对环境检测的。李子轩，李子轩，李子轩，李子轩，你饿吗？饿吗？你等会儿。既然都能就是改变这个状态，但是它有区别。他说这个生理变异了，但是事实上都是改变了这个关系变了，但是像开能变异还是都是人为定义，没什么固定的说法。老师。就是说咱上怎么办？上怎么下怎么办？我觉得这个就出来了。 好是这样。哦，没错，不是这样，是这样。我就把刚让你用把这个带里，把这上一个带里，你就形成了。
所以我们喜欢。
What's up?
So for this, the observable loading the detector is written like that.
Okay.
But what does this mean though?
The +1?
So there's a +1 to this,
Okay.
and then -1. So if I